desktop systems that extrude, like they're basically like hot glue guns on robots. But what we're talking about is actually there's lots of different ways to create an object layer by layer. So there's lots of technologies out there, and we'll talk about them. But in general, what they all have in common is that we're taking a 3D model and we're going to build it from the bottom to the top, layer by layer. There's lots of different ways. And you'll notice the word additive is really critical here because it's to oppose it to subtractive manufacturing, the more conventional, I start with a giant chunk of metal and I'm going to mill or machine away. I'm going to subtract material to get to the shape I want. Whereas here, we're going to add material selectively to get to the shape that I want. So again, in general, what all of these processes have in common is some three-dimensional model on your computer, a digital file, and we're going to slice that into layers and then lay down material layer by layer to build the object. And this is something we've been doing a long time in human history, actually, right? We've been always thinking about creating complex, contoured, three-dimensional shapes by slicing it into layers and then assembling them. So instead of doing the old cartography way, now we're making, contour maps. We've just basically replaced that with robots and shrunk the layers down to really make them very fine, so we're able to create a really nice representation of three-dimensional shapes. So think about it in that context. So again, as I mentioned, we're all familiar maybe with this idea, right? I'm going to feed some plastic in through a nozzle, like a hot glue gun, and I'm going to build this object layer by layer. And this is actually a time lapse from our lab of us printing, of course, the hokey birds. You can sort of see the shoulder, right? The elbows there. And you'll see that black material is this supporting material that we'll wash away. It allows us to create shapes like the turkey neck that overhang and support each other. But we can, quickly make prototypes and objects, right, with this technology. And this technology has actually been around for 40 years now. We're all going on year 50 here pretty soon. But that's just one way. We call that technology material extrusion, right? I'm going to take some plastic and I'm going to extrude it selectively. And we should mention, by the way, that in that phrase, extrusion, there's a whole bunch of materials. We actually have a local company in town, Blacksburg, called Cell Inc., that uses that same principle, but it's printing biocompatible materials. To think about bioprinting, extruding biologically compatible materials that can be embedded in the human body. So there's lots of different ways of that idea of extrusion. But what you might not know is that's just one of 7 different ways of printing. So very big classifications, and there's lots of companies and lots of materials inside each one of these. And they are again, in common that they are able to form objects layer by layer. Some of them are ink jetting processes. Some of them are actually using lasers to selectively melt powder. We have other technologies that actually use ultraviolet light to selectively cure resins layer by layer. And actually, again, another company that we have in town, another startup, uses this technology, vat photopolymerization. So Skyphos uses that technology to make very, very small, very, very precise, like lab on a chip kind of devices. So this technology is not about just making Yodas about yay big, but they can shrink and make things very, very small. But because of our guests here, we're going to be focusing today a lot on this directed energy deposition technology, which is about making metal components at very large scales very quickly. So let me tell you a little about, for example, one quick other technology that just to give you an idea of other ways that we print is this idea of using lasers to selectively melt powder. And we have a technology like this on campus. And it's probably one of the most commercially adopted metal technologies. But again, this is a quick video of what they're using as a laser to actually selectively melt metal powder. And you can sort of see that transition from powder state to a molten state. And then when it's done scanning that layer, that image layer will push powder across to sort of recoat a layer on. And then they'll selectively scan again, and that will melt, again, that area of the layer, but it melts into the previous layer. And at the end, you're almost like an archaeologist. You have to dig through the powder to get your final part. And believe it or not, many of you have flown on commercial aircraft with some components made from this technology. Every SpaceX rocket that you've seen go to space uses printed engines. We're seeing a lot of adoption and, both not even in not just aerospace, but even a lot of medical implants. Some of you might have friends who've had a spine implant or a knee implant that has been printed with this technology, right? So It's not just plastic trinkets, it's actually also high-end polymers and high-end materials, but also metal components. So just to give you a flavor for other technologies. Again, as I mentioned, we're going to focus a lot today on directed energy deposition, which is this idea of directly adding material selectively. And one of the technologies we'll talk about is this opportunity. Imagine just taking a welder, attaching it to a robot, but instead of just doing one line of a weld, but actually stacking the welds layer by layer and building big metal parts out of that. And so Alan Pearce from FasTech will tell you a little bit more about that technology and how his company uses it in the production of large-scale metal parts. Another directed energy deposition technology I'll let Nanci explain is actually a very proprietary technology that actually was commercialized and invented here in the New River Valley thanks to MELD. And it's a really unique technology that takes another joining technique, in this case, friction stir welding, but does it layer by layer to make very large metal parts. Before I pass it off to them to explain their technology and their ideas and markets in more detail, I just wanted to quickly give you an idea of how these technologies are used. So when I first started this technology way back in the day, we called it rapid prototyping. It was only really a technology for quickly making an object, making sure everything looked right, and then sending it off to the machine shop to get made. But now we've transitioned to this world of additive manufacturing, where we look to these technologies to make final parts. So the original idea, and still a very big use of these technologies, is I have some sort of idea. I don't want to invest the time and money and tooling required to make that idea, but instead I want to go to a computer model and then hit print, right, and get a plastic version, a quick prototype, right? And it allows me to iterate through my ideas much quicker, or I can bring them to my customers and show them a model and say, yes, we all sign off on this idea. So it helps with communication aids as well. Again, a very great use of the technology. But then what we're starting to see is people starting to do more functional uses of these systems. So one of the big ideas is maybe I still am going to use traditional manufacturing to make my product, but I have a lot of tricky operations. I have to do assembly, so I have to sort of jig and fixture everything in place, or I have to do very careful inspection. And I don't want to use my manufacturing tools to create these custom odd-shaped fixtures. I can use this technology to sort of design and quickly make those kinds of jigs and fixtures to hold my parts in place during assembly or inspection, or to aid in traditional manufacturing. So that's another big use case we see in this industry. And again, every single one of these is made with a different technology. Maybe some of them are made out of metal, some of them are made of polymer, some of them are made out of composites. Each one has its own pros and cons, and that's something we as a community can work together to help with. The other idea, the other sort of evolution of the technology is what we refer to as rapid tooling, where we're going to actually print a tool and then actually use that in traditional manufacturing to make the part. So we're not making the part, we're just making the tooling and fixturing to finish that. So we might be able to make, for example, a short run injection mold using a polymer additive manufacturing process. So we're just making the mold and then inject plastic to make the final part. There are even technologies that allow you to directly print sand and use it in traditional sand casting. If you don't want to make the patterns and tools, you actually can print the mold directly. And even there are large-scale polymer additive manufacturing technologies that are being used to print very, very large molds, like this wind turbine blade mold, that they can then use to do conventional carbon fiber or glass fiber layup to make wind turbine blades or other very large-scale air structures. So additive manufacturing is not just something that fits on your desk, it's something that fits in half your factory, right? It's very large systems that allow for the manufacture of very large objects. And again, what we're really thinking about, and what often we talk about, is this idea of using the technology to take a design, do the digital analysis, and then take it to production and actually use that on a final object. And I think Nanci and Alan will talk a lot about this instead of these really cute senior design projects from Virginia Tech. The last thing that might surprise you is that these technologies, specifically this directed energy deposition technologies, are really unique in that they're also able to repair parts. So it's not about just making an object from nothing. You could actually bring an existing object into your printer and repair or deposit material to repair holes or other damage. So for example, I might have this toothed gear here, and I can actually go in, with a directed energy deposition system and selectively weld in and add material, and then actually take it now to my machine shop to remove material. Or again, re-tip turbine blades, for another example. And maybe Nanci will share some of her company's work in repairing, aircraft components, that otherwise at that damage would have to be thrown away and started from scratch. And here we're able to just directly use that technology to add material. So what are the value propositions? And I think this is a good opportunity to let Nanci and Alan, so I'll just run through these. I think the bottom line here is we have an opportunity with this technology to digitally design and manufacture objects, which allows us to reduce the delays between new ideas. This other idea is that complexity is not necessarily free, but we're able to make much more complex and lightweight components than other traditional manufacturing processes will allow, because we're able to sort of grow parts and not have to reach in and subtract and mill away. We're able to make lots of parts in a single print that are all unique. And some of your friends might have custom-made hearing aids. Almost all the hearing aids now in production are all 3D printed, right? Because each ear canal is unique. Some of you might have the Invisalign orthodontics. Those are also printed components. And this idea that we don't have to delay manufacturing, it's very agile. We have a single tool to make almost any shape, and that saves a lot in production time and training. And one of the really nice things, it also reduces assembly, because again, that complexity allows us to make a single part where maybe we had to make several components and then have to assemble them together. And one of the things that we're excited about is limited waste. So, if I were to take a traditional part that I would like to achieve, this part over here, traditionally I would take a giant block of metal and waste almost 20-to-1 ratio of the raw materials on the floor to get to the shape I want. Whereas an additive, we're able to get a much better buy-to-fly ratio, meaning the amount of material I purchase actually ends up on the part instead of just waste on the floor. And I think what you're going to hear from Alan and Nanci is that what we're really seeing right now, especially in the world of large-scale metal additive manufacturing, is that there's a lot of demand for large parts that are traditionally made through castings and forgings, and there's a huge supply chain limitation there. And now their technologies are providing answers to address that. So with that, I'm going to skip my last slides and just pass on to I'm going to keep calling them our assets, our key partners in our region who are really leading the industry with their representative technologies and services. So we're really fortunate to have Nanci Hardwick, who's the CEO of MELD Manufacturing. I refer to, that is what we would call an original equipment manufacturer, someone who actually manufactures manufacturing machines. And we have Alan Pearce, who's CEO of FasTech, which is located in Danville. And they use existing, machines to actually provide a service and actually design and fabricate and qualify parts and large-scale metal components. So with that, Nanci, I'd like to invite you to jump in here and tell us a little bit more about MELD and what you all are up to.
Okay, thank you very much. Let me share my screen here. Okay, can you see my presentation? All right, great. Thank you, Chris. I think that was a great overview. I would echo that there is a ton of variety in that additive manufacturing space. Like any manufacturing challenge, there are many tools to choose from to solve the problem at hand. The same is true in 3D printing or AM technologies. So MELD is certainly one route for AM, but there are many, and they all have advantages and unique attributes that make them appropriate for certain products. So I would be really excited to tell you about my company, MELD Manufacturing Corporation, headquartered in Christiansburg, Virginia, tell you about the MELD technology and why we're doing what we're doing. So let's start with the why. It is our mission to disrupt the manufacturing and repair of metals to serve humanity with the power of 3D printing, both here on Earth and in space. As Chris mentioned, we are an equipment manufacturer, so we will do this by delivering equipment using our award-winning patented technology. And that technology is meant to print any metal at unsurpassed speeds, meaning very high rates, at any size with forged properties. So that's our unique value proposition. I minimized the videos in this presentation in case we had some trouble with internet speeds, but I wanted to show you a part right out of the gate. And this is being printed on a MELD machine here in our facility. And in case that didn't come through or you're wondering how big was that, here's me with that part. This is about 20 hours of printing and almost 300 pounds of aluminum. And I think this is a great example part to show you, to give you a sense of what MELD is capable of. So we're specifically having a tremendous amount of pull from industry for large metal components that previously were manufactured from forgings. And you have probably seen some of these headlines yourself, but all around the world, innovators and manufacturers are having challenges getting large components in a raw form to be able to make their products. And so large metal parts, as Chris mentioned, usually come from a big block of metal that has to be then machined out. And sometimes, 80% or 90% of the metal is being machined away to get to the final geometry. This is where we can add value for a number of reasons, but certainly saving material and being sustainable is one of them. So here's just an example, a model of a component used in the semiconductor equipment business. This is a large square with some features on it made out of aluminum. The block of metal normally costs $30,000. And then to machine away most of that metal into the final geometry is almost as much money. It's about $22,000. That's all fine and good, except this company can't even get the block of metal to make the part. So right now that lead time is almost a year. And I'm personally hearing customers say 1 year, 2 years worth of wait for blocks of metal to even begin the machining process. And when you're doing that much machining, the machining itself takes quite a lot of time. As you can see here, we're talking about 20 weeks of time just for machining. So this is a relatively low count need at 40 a year, but this could be a showstopper for an industry that we're all relying on to grow and to provide chips. When they came to MELD, we were able to offer a component in weeks of printing time at a total cost that is less than today's billet cost. And this is the advantage that you will see over and over again with 3D printing. It won't always be cheaper. It is a new technology, and new technologies have a cost to them. But there are opportunities to not only save material, not only save time, but save money as well. So what is unique about MELD? There are a few things. The technology that we have created has some unique attributes that let us print in materials that are not otherwise printable with other 3D printing technologies. We have a lot of activity in aluminum alloys. Magnesium alloys are another material that I don't think is otherwise printable. Copper, titanium. These are the materials that we have the most pull for. The size, as you can see, there's really no limit on scale, and the speed by which we can make these parts. It's quite high. We have a very high deposition rate. And hopefully you can see this printing and you can tell that we're printing in just an open air environment. Because we don't have to be in a chamber, we have the ability to scale up the equipment and thus make parts that are as big as the equipment can facilitate. There's a little bit of explanation of our process on this slide. What we're showing is the use of solid metal bars going through the machine. And you can see the rotation, and we also use force to put enough energy into the material to get it to plastically deform, but we are staying below the melt temperature. And this has some other benefits as well. This is essentially how we're getting to forged properties and usable material right out of the machine. As I mentioned, this is very unique. We have over 24 patents in the US and worldwide, and I'm very proud to say that this technology was invented in Virginia and in your hometown. We've received a lot of recognition for this technology. We have a number of awards, both international and national. And just this year, we won an award at the Military Additive Manufacturing Summit for technical achievement with our partners in the U.S. Army, as well as other partners listed on this slide for what we all believe is the creation of the world's largest 3D printer in metal, which I'll show you in just a moment. So with that background, I thought I'd give you one more, take a chance on the internet speeds and give you one more video of printing. This is obviously sped up, but we're putting down about 20 pounds per hour of aluminum. So very high deposition rate. And you can see these are more simple geometries than some of the other things that Dr. Williams showed in his slides. So again, I feel MELD answers the call for billet replacement and forging replacement. As he said, we are an OEM. We manufacture equipment, and these are some of the machines that we offer from our facility in Christiansburg. Just to give you a sense of scale, this is our smallest machine. So you are looking at a 3D printer in this slide. And Thursday, when you come to visit, you'll be able to see this printer in action. So our L3 model, I did name my machines after droids in the Star Wars series for Star Wars fans. K2 is a bit bigger, about twice as wide and a little taller, so you get a sense of being able to print larger components. And then 3PO is our first hybrid machine, and that means that the machine can both print a component and then mill or perform subtractive machining on that component. So you will be able to print and then machine down to your final geometry. And this is a really large machine. This is the largest that we manufacture ourselves. However, we offer the MELD hardware as a retrofit so that if you need a machine that's bigger than we can manufacture, you can work with a machine platform manufacturer to integrate the MELD equipment, which we just announced a relationship with Fuka in Germany for this purpose. So they will have a MELD product line of their own with much larger machines. Another example of that is a machine that is now housed near Detroit and operated by SAE on behalf of the U.S. Army. So this machine is a hybrid machine. It has MELD hardware for printing and a subtractive machining center. You can print and machine down to your final part geometry on this same machine. And I included Mark Pickett's contact information here. The Army set this center up specifically for collaboration with industry to utilize the MELD technology. So Mark would welcome your inquiries if you were interested. This is what I believe to be the world's largest 3D metal printer using the MELD technology. As I mentioned, this is a project that we worked on with the U.S. Army We were very excited to be selected unanimously by the committee choosing a technology for this printer. Obviously, being able to make big things was a big advantage for the MELD technology. You're looking at a 3D printer that can make parts that are 12 feet tall and 20 feet wide and 30 feet long. A tremendous printing capability. And you might say, I wonder why they did that. What were they thinking about printing? The motivation was to print entire, or have the ability to print entire structures with absolutely no seams whatsoever, no welds, no weaknesses from traditional manufacturing, to offer the most ballistic protection possible in structures such as the vehicle you see here. And so this is that machine for scale with myself and the MELD user group last November, and the beginning of a part printing in front of us. We've been very honored to be a part of the program, and I can't wait to see what comes out of that printer. So many people, the U.S. Army was the first group to put this in writing about the MELD technology, but it's something that I get to hear a lot. And now I'll just show you a couple parts. This is a tank hatch that we made for the U.S. Army. This is a radome mold that we made for the Air Force. And I like showing this part because it shows a couple things. First, it's another example of a low rate need where time was critical. And second, you can tell that the finished part came from two things: the printed material on the surface of a block of metal, and then the block of metal itself. Normally, this part would come from one giant block of metal. So this is a really easy way to conceptualize how A, we're saving material, and then B, how we're saving a tremendous amount of chip making or machining to get down to the final geometry. We've been working with Boeing and our university partner in Tennessee on landing gear components. So this is an exciting part because it's made from aluminum 7075, which is an unprintable material, except for the MELD technology. We've been working with our space customers on components, pressure vessels and domes. We have other activities for the Air Force, creating parts that are needed for maintenance and repair operations where there isn't an inventory and perhaps the original manufacturer doesn't exist anymore. And then I think another fun one here is just for you to see how being able to use the plate that's printed on and the printed geometry can yield something very exciting. So at MELD, you'll see some fairly basic shapes being printed, but they turn into very exciting components. And so now we're looking top down at a half machined part. This is a wheel, and you can see the as printed side on the right, and then what it looks like when the machine goes through a milling process or subtractive process to get to the final part geometry. So a few examples without any videos of what parts look like, a very wide variety of industries coming to MELD for these parts. I showed you all 3D printed components, but Chris did mention repair. And I think it's a great way to contribute to sustainability by being able to replace, repair, recoat material in components that are worn or damaged. And in the case of this magnesium gearbox housing, which is a flight critical component. There is a standard crack that occurs, and MELD was able to demonstrate that we can successfully remove the damaged material, print new material with sufficient bond strength to the part itself, and machine it to its original geometry and put it back in flight. I thought I would finish by just sharing some of the activities that we share with the next speaker and with Virginia Tech and others in the state of Virginia. We're very proud to be a part of the Navy's Center of Excellence for Additive Manufacturing in Danville, Virginia. And this picture is from the ribbon cutting before there was any equipment there at all. Right behind us is a 10-foot diameter cylinder printed with the MELD technology. And we've been honored to be a part of not only providing parts for the Navy, but also for workforce development. It's a really great vision and a privilege to be a part of it. Once the equipment got loaded, it looked like this. And then it was my pleasure to explain our technology to the U.S. Secretary of the Navy. So I think that's probably a great place to let Alan pick up, and I look forward to everything ahead for all of us. Thank you.
Great, thanks, Nanci. All right, Alan, if you'd like to go ahead and share slides, or and we'll go from there.
Can you hear me okay?
We can, thank you.
Super. Okay, thanks, ladies and gentlemen. Nanci, I can't really beat that eloquent presentation, but I'll do my best. So we are based in Virginia as well. We are down in Danville, Virginia, which is ironically a good lead-in, as Nanci said, to where and why we're there. I chose Danville, Virginia, because of its excellent training facilities, and we are fundamentally an old machine shop that used to manufacture parts in the UK and America for the aerospace industry, particularly, and DoD. And I wanted to invest in this additive technology because I could see the huge savings in cost and lead time. So we went to Danville and we used their program to take young engineers out of and turn them into sometimes attractive or additive engineers. And that's been very successful. And that's why we've been fortunate, like Nanci, to be connected into the Centre of Excellence, which really came out of a visit we had from Admiral Capono a few years ago when he saw we were using welding to manufacture parts for Siemens Energy. And he said, well, why aren't we using this technology for making parts for the ships? You know, here we are now, 3 years later, with a Centre of Excellence with a machine inside it, which Nanci's provided, she showed you, along with some of the other technology we use and other powder technology. So it's been a phenomenal investment, hundreds of millions into the region for training and additive manufacturing technology, investigation and expansion. For those that don't know, we're close to Greensboro and 2 hours away from Charlotte. Our current facilities is literally connected to the machining program in the cyber park in Danville. We currently employ 18 people, and our planned growth is to 50 by 25. I think the rate's going now probably be more like 100. We're already planning to move into our new state-of-the-art facility across the road, right next to the COE facility Nanci mentioned earlier. And our largest customer, it has become a DoD, I suppose, really, between the Navy and the Army, but also a lot of aerospace clients that I'll mention. We're a service provider, so we use additive technology as part of a solution to be able to print, machine, inspect, and test parts on behalf of the customer. So we're a supplier that would buy, hopefully, for example, a MELD system for some of our clients and opportunities within the DoD arena. Customers that we currently deal with, our largest was Siemens. It was the first company we started with down in Charlotte, manufacturing large gas turbine components for those guys. Nanci, we mentioned earlier, Collins, we do aerospace components for, and Norfolk Space, solar power again. Rolls-Royce engine parts and so on and so forth. And we just started moving into the space industry now as we've gained some traction and some technologies. That's something we're very proud of, and I think it's important to know a little bit about anyone that doesn't really know much about additive. Is that the federal government behind additive manufacturing and they created this AM2 program about a year and a half ago, and I was very lucky to be invited with CEO of Siemens Energy to present some components that we've manufactured using our technology that we currently have. And these parts for the gas turbine engines. The aim for initiative is all about supporting small companies like ours to work with large companies like Siemens, and they are looking at areas of requirement for the market, like qualification, which is a big headache that Nanci will know about, proving that this capability of manufacturing using this technology, also assisting small companies to be able to buy equipment, because it's multi-million-dollar investments. And the big other leg of the chair is training. There's no point in creating all this technology if no one's got the skill to actually make the parts. And in Danville, the new facility for training additive, welding, machining, and inspection of additive and other standard parts will create over 1,000 trainees just within the next year that can come and work for companies like ours and MELD, and obviously the supply chain that feeds into DoD. We touched on earlier about what's the difference, and Chris did a good job of covering that really. So what's the difference between standard ways of making stuff and our way, like additive way? And there's lots of conventional manufacturing processes that go into manufacturing a component. If we look at this picture here, you'll see all these different processes that typically you'll use to make a single part, and a conventional process, and we take that down to 3 using wire, a machine, for actually printing, and a machine to maybe post-process or finish the part, if you like. And whether it's wire feed or bar stock as MELD use, the principle is it's easy to buy off-the-shelf material globally, and that makes such a difference to the supply chain issues that are common all over the world now, but particularly in the US as we start to reshore, which is good news. Technologies that we use are wire-based DED, and as you know, Nanci's covered the MELD sort of product in terms of printing raw materials. There are technologies out there that use powder, which we choose not to use, and that's purely on the basis that we're looking to make big parts for industry, not small parts. And this technology lends itself very well to that industry, such as MELD does, as Nanci showed us earlier. So wire versus powder, why do we use wire? It's much more efficient, it's 100% efficient wire. Powder, in the process using powder, is sort of waste. There's a lot of ecological issues, and it's expensive. It reduces contamination risk and so on and so forth. So there's challenges with powder, but at the end of the day, there's a need for that because you need small, fine, high-class parts for aerospace, et cetera, et cetera. So it's not a market that we've explored yet. How does it work? Well, in very simple terms, the customer will give us a shape or a model, as we would call it. It might be a part that they've given us that we scan. Then we'll print to that model and create a near-net shape component. Then we'll scan it, and then we'll machine the part, and it's finished. And that's our kind of like our workflow for the process we use within our business. And what you can see here, what you will see, hopefully, if the video is working okay, is an example of an aerospace planetary greenhouse, and it's actually Bell helicopters, where we're printing a large aerospace component for them. Just gives you a flavour of the definition that we'll print to. And then this is where we use a laser technology, which is a lot slower, but gives much finer detail if the customer's looking for what would be a very near net shape. So it's like close to form, where we might not need to machine it at all, or there's very little machining, so there's a big cost saving there. So it really depends on the business and the customer requirements. Let's just run through some stories really on what we've made with customers that we've worked with. This is a great example, and both of these guys have touched on this, but waste, cost and waste. You can see here, if we took that raw material block and we machined it all the way conventionally, turned it into that part on the right-hand side, you create There's 6 boxes of chips, as we would call them, 6 boxes of material that weigh 147 pounds, 80% waste. That's wasted. So we've actually used power, and we've used a huge machine to machine all that material away, and it's going to have to be recycled at enough cost, and a considerable cost to actually generate the part in the first place. We'll print it in the next shapes, the picture from the left, and we'll machine it away, but not mass reduction in material removed. So now we're at 28% waste. We've gone from a chip weight that's 20 pounds versus 147 pounds scrap, as we would call it. That gives us the ability to reduce waste, but also reduce cost. And you can see here, the cost of this particular part saved 51% in its process overall. So there can be benefits in cost as well. But I would absolutely, Nanci, the biggest advantage of this technology is lead time, particularly in aerospace and exotic materials where you can't freely buy them. And this is the last part for Siemens Energy, where we've taken the CAD and we've either used the WAM technology to wire art print it, or we've used the laser technology to print it to near net shape. And that gives us the option to either make a part super fast or make a part a lot slower with laser, but give the customer much better definition, which is a need for some customers that require that with castings. So if you look at the process we're using here to produce that part with the art method, you can see it's a lot slower than the MELD process that Nanci's shown you, but what you will be able to achieve is good definition. So it really depends on the kind of part that you require, which is why you need all these different technologies. I guess we're in the medium bracket, yeah, and MELD are in the large bracket. They're like, as you can see, big as a tank. We're probably making parts that go on top of that tank, which are lighter, but not easily to machine out of a large block of material. Then what you're going to see here is the same thing again, but using laser. A lot slower, but you can see there's a lot more definition, so it's a much finer finish on the part, and that allows us then to not have to machine or cut around all of the features on that part, which is a huge saving in time on a very large part like this. When you look at the part when it's finished, you can see there's a nice shiny part there, but a lot of cost into machining that. That's hundreds of hours of machining, and if we use a laser system, it becomes hundreds to 50 hours, for example. So it really depends on the application, but both technologies do lend itself well to our customers' needs. Here's where we just use the technology, laser technology, for inspection. So once we finish the part, we'll measure the part, make sure it's right size, best fit it, and that's a technology that's critical to our flow of work in our business. It's an important part of our business flow. And going back to this case study I mentioned earlier, this is a good example where we've taken a component that with a lead time that used to be nearly a year to actually buy the forging to make this part. Now, we printed that substrate, as you can see that at the top picture, in 18 hours, and we printed onto the rolled plate, which is like a plate that we've already rolled, and did it in 4.5 hours. Either way, we can print the parts so we're near that shape in a day, rather than having to wait maybe a year to actually source that material. So what the customer currently does is they stock over a year's worth of material. So there's hundreds of thousands of dollars of material sitting in a warehouse in Charlotte. They don't need any of that now. So there's a big saving in stock as well as everything else. And that's the part actually printing, if you can say that. And again, that's about 4.5 hour cycle time. And the one in the picture that's finished is actually the one that we've kept, that one because the president actually's got his fingerprints on it. So we're still trying to get them off so we can use it for our own secure reasons, but it hasn't worked so far. This is just another example of a large part. I mean, it's hard to see the definition in video sometimes, but again, it's a large stainless steel part where we're looking for definition. And that, in that particular case, the forging, which was from Germany, was taking over a year and a half, and we were manufacturing that part in about a month. total from A to Z. I think this is an interesting component because it's a titanium part. So that is actually a part, or an example part, again, that we presented to the president, that is a really cool part. It actually is part of a Rolls-Royce engine, and it flies on the Airbus A350, the new plane program. And that is actually in flight test. So when people question, so, you know, this additive technology, does it really work? Well, there are parts now in planes that are flying, titanium parts, which are important, critical parts that are approved and flying around the world with Boeing and now Airbus as well. So it's not just a new fad or a crazy idea that might work. It's real, and it's faster. You know, we made this part in 12 weeks. That's the whole program time. It would take over about 9 months to manufacture that part, because as Nanci said earlier, the large blocks of material, whether they're aluminum or titanium in this case, can take many months to source. Unfortunately, a lot of it comes from China as well, which doesn't help. So we'd rather buy wire within the DFAS community, which is America and European countries. It allows us to use, let's say, Western wire sources to print material, rather than having to rely on Asia or Russia for the source material, which is, I think, is good news. Here's a nice little naval propeller that we've done using the laser technology. That's a stainless steel part, if anyone cares. So I think in summary, we do a mix of services. I mentioned earlier, kind of an A to Z service, and as we grow, we intend to invest in qualified equipment like MELD to offer services all over the US, as well as hopefully worldwide. But you know, we're in it for the long term. I truly believe that this technology is here to stay, and it is now growing exponentially. So I think it's a great thing for Virginia, and I think we've got to be behind this, because we could be seen as the pioneers in this technology, in terms of not just, I think what we've got right is we're not just doing R&D anymore. We're making parts. You know, we're delivering parts, and we're training people now. You know, and we're held. They're building machines that feed into the ecosystem. So we've got some really exciting things going on. You know, and I truly believe that this project and bringing it to Virginia is a highly valued investment, and I'm right on it.
Great. Yeah, that's awesome. Thank you, Alan.
You're very welcome.
And thank you, Nanci. So we know that we are running short on time. I want to give everyone a chance to ask Alan and Nanci questions you might have. I hope the big takeaway is, maybe our first goal was to make sure everyone understood that, you know, what we all understand or know as 3D printing has grown quite substantially. And we're seeing some real actual parts being made and manufactured here in the state, and more specifically in our region, thanks to some really key assets that we have. I want, as we're sort of waiting for questions to come in the chat, maybe Nanci and Alan, if I can ask you one to quickly, this is a big question, but try to make it short just because of time. But, we've heard from, an OEM, we've heard from a service provider. Tell us a little bit more about the ecosystem of a neighborhood, like, that we could build as a region. Like, what are the other needs? What are the other opportunities for all the companies and partners that we have in our region, in this space? Nanci, do you have any thoughts on that? Like,
I do.
Yeah, go for it.
I am so excited about the potential for our region because of our heritage in manufacturing. This is an opportunity to take what is already a strength of our community and use that strength to propel us into the next generation of manufacturing. And as Alan said, to be pioneers. There's so much opportunity here for us, and I hope everyone got the idea from these presentations that this is just the beginning. A lot of industry pull is for existing parts made in a new way. And where we will get to very quickly is making new parts in a new way and really unlocking all kinds of potential, from new alloys and multi-material components to completely new designs. For that, we need so much more. Having the equipment is great, it's not enough. Having service providers is great, it's not enough. We need machine shops and service facilities that get parts to their final shape and form. We need companies who are expert in QC and inspection technologies. We need engineers and designers to help us go from knowing how to make it with traditional methods to these new methods. And we need our workforce development. We need every partner that we can get to help train everybody, from the guy in front of the machine to the guy at the desk in front of the CAD to the person designing the product in the very beginning. There's, what I've learned in my time in additive is wherever we get to, our customers say, wow, that's great, thank you. Now we need you to go farther, faster. We need bigger. So our university partners will always have so much research to do to help us figure out, how do we move to the next alloy? How do we go bigger? What are the properties of these metals? What is the art of the possible? So there's a lot to do. There's a lot to do, and many hands are needed.
Great. Alan, your thoughts?
Yeah, lots of answers by Nanci, but I think there's a need absolutely for services. So qualification is the biggest issue in our industry. Prove it. Does it really work? All that good stuff. There are no standards. So working, and when we can't create standards quickly, so working with customers and potential I suppose opportunities, like even with the DoD, where they want to qualify quicker than waiting for some global standard, then any support to do that with universities, tech centers, hubs, whatever you want to call them, is more than welcomed. I think we need that support and the only way to do it is with customers. We can't wait for the world to fix it and create these wonderful additive standards. We can't wait, so we got to do that. We can do that with you guys and all that good stuff in Virginia, I hope. I think the training side is obviously critical. We've started it. Someone asked about graduates, where they're heading to. Already we've taken 5 graduates out of the latest additive program working for us right now today. But they are feeding into Virginia generally. And if there isn't work in Virginia, they'll go all over the country. It's Navy obviously driven, so they'll tend to go up into the yards, or they might go down to Alabama, where they're doing a lot of shipbuilding as well. So I think that's super important. And also things like heat treatment and inspection. These are 2 things that we have to have. And us little small companies can't afford these huge CMM machines that cost millions of dollars. So in my opinion, give me a company that's in the hub of Danville, for example, that we can all share, right? So we need shared services, and we got to stop being so defensive and secret about what we do in our industry. If we want to advance, we got to do it quicker. So we need all those things. Oh, Chris, you're on mute.
Perfect. Yeah, thank you. All right. I see Mark had a question, Mark Mondry, which was, for both of you, what do you think is the biggest obstacle to growth? Maybe both for your company, but also, that might prevent our, from the regional standpoint as well. What do you think the biggest obstacle is? Alan, do you want to start?
I'm going to start with this one because I've got to get off my chest. Money, right? These machines are millions of dollars, and I've invested millions in these machines. We will invest more, but we have to buy it and improve it. So I don't have all these orders waiting around me so I can buy a machine and just fill it with work. So we need support in being able to borrow money to buy machines like Nanci's, yeah, because it's really hard, especially SMEs, especially small companies like mine that are growing. So that's a big one for our company.
Yeah. Nanci, anything? Your thoughts?
What I see as a challenge for growth, especially here locally, is a program to introduce additive to existing manufacturers, particularly small manufacturers, and to help them explore what the benefits are, and probably underwrite some of the cost of that investigation, until they can build enough education to be comfortable with this new technology.
Yeah, and then to that point, Alan, you had mentioned the AM4 initiative, which is a federal initiative, and we have colleagues here at Virginia Tech who are also working on other projects to help small and medium manufacturers to find their way into this supply chain. I know we have lots of other questions, and Sarah, I will follow your lead. I do want to acknowledge really quickly that the other, another part of this tech hub is, of course, advanced materials, and it's not only metals materials. I'm looking at Bob Moore, who's leading our polymer program at Virginia Tech, and of course, additive is much larger. As we've said, so many applications and so many different technologies. So it's not all metals, it's not all large scale metals. It's also, I think, as I acknowledged Elliot before, his company does a lot of very small, very precise advanced polymer material. So there's lots of other topics to talk about as we go forward. We have other great companies in the region who also provide polymer solutions, and maybe even ceramics or glasses, all of which have been printed and provided our region another area in which to continue to grow and be a hub. Sarah, of course, I want to get to Elliot's question, but I know we're out of time, so I'll shut up and let you sign us off.
Yeah, sorry about that. And we will get to all of these questions, and this is only just really the beginning of a conversation. We will continue on with a lot of these kind of 1 hour discussions about additive manufacturing and about materials. So keep your eyes peeled for future events. And please, for discussions to continue this week, come to our all hands meeting on Thursday starting at 1 o'clock at MELD, followed by going to the county center and going to and having a discussion about the larger needs of the region around additive manufacturing and applied materials. Thank you everyone for attending. Want to respect your time and have a good rest of your day.
Thank you.
Thanks, everybody. We'll answer the questions as well. We'll try and do that if I can, Sarah and Chris.
Yeah, thanks, Alan.
Definitely, yes. Please follow up. We'll send out some emails.
Thanks very much. Lovely to meet you all.
That's you.